Hello, everyone. My name is Jiho Shin in Samsung Research Language Intelligence team. I'm going to introduce the topic on-device translation with AI together with NTN Hu. This is our contents. I will present on the first and second chapters, and NTN Hu will present the last chapters. Overview of on-device machine translation. In an increasingly interconnected world, communication across language is essential. Whether it's international business, education, or simply traveling, translation bridges the gap between different cultures and languages. Without translation, sharing knowledge, ideas, and innovations across borders would be nearly impossible. So translation is a key driver of global communications. As the world continues to globalize, the role of translation will become more important. In the digital era, translation is the key to breaking down this language barrier. With the explosion of digital contents, the need for real-time translation is also growing rapidly. For example, on platforms like social media, news, online shopping, and gaming, people encounter contents in various languages. Without translations, these global experiences would be limited. So translation is not only a tool, but a necessity. Then what is machine translation? Machine translation is the process of translating text from one language to another. It involves the algorithms and artificial intelligence to translate content without human intervention. Machine translation systems are designed to understand and reproduce the meaning of the original text while maintaining the correct grammar, syntax, and style. The history of machine translation is a fascinating journey. The 1950s and 1980s saw the development of rule-based machine translation, which relied on complex sets of linguistic rules and bilingual dictionaries. This system required extensive human labor to create and maintain the rules and dictionaries. In the earlier 1990s, a new approach, statistical machine translation, appeared. This method relies on large corpora to model translation process. In mid-2010s, neural machine translations appeared and revolutionized the field. Neural machine translation uses deep learning techniques to model entire translation process. Neural machine translations is much more natural, resulting much more natural and fluent translation results compared to SMT. Now, let's talk about two primary types of machine translation. One is cloud-based, and the other is on-device machine translation. Cloud-based systems rely on remote servers to process and deliver translations. This method is popular because it leverages a large-scale neural network. Additionally, however, it has some drawbacks. It requires a stable internet connection, which can be an issue in remote areas or during travel. Moreover, transmitting data to external servers raises privacy concerns, particularly when sensitive information is involved. On the other hand, on-device translation works directly on a user's device without the need for an internet connection. Then what are the advantages of on-device machine translations? The first is security. Since all processing is done locally on device, no data is sent to external servers. This is crucial for sensitive and confidential information. The second is reliability. On-device machine translation doesn't require an internet connection. This makes it extremely valuable in areas with poor connectivity or when traveling abroad where Wi-Fi or mobile data connection may not be available. Whether you are in remote areas or simply don't have access to internet, on-device machine translation ensures you can still communicate. Now, third is slow latency. On-device machine translation eliminates the need to data transfer to cloud server. This meaning translation can happen almost instantly. This is particularly useful in real-time situations. Finally, on-device translations can reduce costs. Cloud-based translations often incurs ongoing expense. With on-device translation, there are no server costs or subscription fee, as everything runs locally. This can significantly reduce cost over time. On-device machine translation offers significant benefit as mentioned in the previous slide, but it also comes with several challenges. First, we have limited computational resources. Mobile devices generally have less processing power compared to powerful cloud servers. This can lead to slow down translation speeds and reduce the translation accuracy. Additionally, memory constraints are an issue. On-device model need to be small enough to fit within the device's limited memory, and this often requires heavy optimization, which can compromise translation quality. The second is model optimization trade-offs. We often reduce the model size using techniques like quantization, but this can result in a loss of translation accuracy. The third one is energy consumption. Running intensive computation on devices can drain the battery quickly, particularly in continuous or real-time translation scenarios. Lastly, there is the issue of model updates and maintenance. On-device models need to be periodically updated to improve their accuracy. Managing these updates can be challenging. So, how does on-device machine translation works? In the next chapter, I will explain in detail how we developed our on-device model. I will address the challenges we faced in order to make our translation model available for live scenarios. I will start with how we trained and made the quantized model. Then I will move on to what we did to give the compact size model a great performance in translation. Finally, since our model was used in various application scenarios, such as web translation, we enhanced the data set, thereby improving translation quality. I will cover these topics one by one. We applied quantization to compress the model, and this method is called binary coding quantization. It is a method of compressing multiple weights using a few 32-bit variables and a number of binary variables. This allowed us to significantly reduce the size of model. It also provides computational benefits. There are limited cases for binary weight combinations compared to 32-bit size data type. The identical computation is performed repeatedly. By constructing a lookup table for this, we can eliminate costly multiplication operations. through indexing operations. We can also calculate matrix computation using compressed weight. This means we don't need to decompress the weight during the inference time, so we can conserve both decompression costs and memory usage. Next, the accelerate inference. CPU inference takes longer because of cache misses in embeddings operations. Because the embeddings matrix is relatively large because it contains tens of thousands of vocabularies. Also, the number of parameters our on-device model has is only tens of millions rather than upon billions from other large language models. For our models, embedding the computation takes up a large portion of the entire computation workload. According to our profiling results, embedding operations account for approximately 40% of the entire latency. So we have developed locality-sensitive hashing algorithm for our quantized model. We improved the inference speed by selecting tokens with the highest similarity using fair computations. And then we perform the final computations on these tokens. We can accelerate inference speed. With these methods, we are able to compress the model, reducing the size by 87% and latency by 43% on-device CPU. I will introduce the training process we use to improve the model's performance. When you train a model which has fewer parameters and make it even smaller by quantization, the performance is poorer than when you will get from the bigger one. This is why we have applied a training process with multiple steps. The first, we train teacher model that has a lot of parameters. After that, we train student models using knowledge distillation from teacher model. Please note that we don't quantize this at the same time. The training is done in 32-bit data type. After training the student model, we take the trained checkpoint and proceed the quantization-aware training. Through this process, we can boost the performance of the compact model running on device. At the same time, training data is also important. So we collected high-quality parallel data or mono data from different domains by working with other teams. So far, I have introduced our training, compression, and inference process. From now on, I will introduce how we solve the problems related to data. The web pages we see are not only made up of plain text. As you see in this example, there are tags in different places in the sentence, such as bolding style tag or hyperlink tags. The data we use for training is only made up of plain text, so we needed to make this type of data set. One of our main applications is web page translation. We have to find a way to process such inputs effectively. Before the model was improved, the translation required splitting up the inputs whenever the tags appeared. So the model has to work on the split up data. You can think that the translation quality may not be good. So we created a data set like this type using word alignment techniques. So using this training data, we can train the model to translate this type of inputs. I brought an example from Wikipedia to show you the difference. This translation result when I search for San Jose on Wikipedia from Korean to English translation. The image on the left shows the result from the model without data, and the one in the right, and the right one shows the results with augmented data. You can see that the problem has disappeared and the translation is more natural. By applying the previously explained data augmentation method, we are able to add features to another application scenarios. This input included emojis in the sentence. Such types of data can also be processed similarly to web tag sentence. So this wraps up the section about our translation model, and Etienne, who will present the last section.
All right, thank you, Jiho, and hello, everyone. This is Etienne Hu from the Language Intelligence team at Samsung Research. In the following section, I'm going to share our solutions to on-device translation service. So from our previous slides, we can see that AI models play a critical role within the on-device translation service. However, to deliver such fabulous models to the real world and push the translation quality to its limit, additional solutions are also necessary. Therefore, I would say solution is the bridge between the real world and the translation models. In the following section, I'll try to introduce our language detection module, the pre-processing and post-processing of the translation module, and our strategies to the development of its infrastructure. So let's get started with my first topic, language detection. I know that some of you might be curious about the relationship between the language detection and the translation. Well, both source language and target language are needed for translation, but in some cases, like foreign website, it is difficult for the applications or even humans to figure out which language the input sentence is in. So I would say the language detection is the starting point of accurate translation, and I'll try to cover these three items for this topic, which are our model and the difficulties to language detection and how we overcame them, and how these language detection modules work with our translation service. First, our model is designed with the structure to learn text classification and word repetition. We also made sure that it is light enough to fit on the mobile devices. The size of our model, after compressed with weight quantization and feature selection, comes to 3 megabytes. We trained it to identify 83 languages, and with our evaluation test set, the accuracy of it is approximately 97.7%. Identifying language simply with the model itself is far from perfect. So in this slide, I'll try to show you some difficulties to language detection we have encountered so far and how we overcame them. And as the key I mentioned in the slide, the core concept of our strategies to overcome these difficulties is filtering any noise that might interfere with the model. The first difficulty we have found is with sentences composed of several languages, which are common in the online encyclopedia. Therefore, we added a preprocessing module to decide the importance of each part of the sentences and remove the less important ones. The example here is to remove the additional information in the parentheses. The second problem we've encountered is the elements not belonging to any language, like email addresses, URLs, or HTML tags, which should be neutral when it comes to language identification. However, the meaningful words within them sometimes affect the language detection model and its accuracy. So our solution to this is to find out these patterns in the input sentence and try to filter or simplify them as the example shows. The last difficulty to language detection we would like to share today is speech patterns which might break the grammar rules. For example, the repetition during conversation to emphasize something sometimes breaks the grammar and affects the accuracy of language detection. So for this case, we added a component to remove such repetitive patterns in the input sentence. With the preprocessing and the model prepared, the last step for the language detection module is to get ready to send the results to translation service. Here are the two targets we focus on at this step. The first one is the supported language adapter. Currently, our language detection model supports a little bit more languages compared to the ones offered by the translation service. Therefore, we applied this adapter with strict exception handling to prevent the translation service from receiving the languages it doesn't support. The other target is user experience optimization. Here we have an example for locale flexibility. When the language detection module finds that there has been some translation service in the same language of some locale installed on the device already, it will try to return the installed locale as the identification result. The reason that we take this strategy is that the performance of the translation models is in the same language is quite similar, and with this scenario applied, the efficiency of device storage can be improved. Users can have better experiences without being redirected to any unnecessary download pages. Similar to language detection module, applying pre- and post-processing to models can improve the translation quality. As the subtitle says, getting the input sentences well prepared can perfect the translation. Therefore, I will try to share 3 of our pre- and post-processing strategies to translation module in my second section, which are rejection, text and placeholders, and formatting normalization. Rejection ensures that only accurate and reliable translated results reach users. And based on our observation, here are 2 cases where translation models might not work as we expected. The first one is when the sentence comes without any semantic element. For example, the sentence is composed of only symbols. Even if we can train the models with those symbols, it is not 100% guaranteed that the training data can cover every combination of those symbols. To prevent these problems from happening, we added a module to reject the sentences matching those patterns. The second cases are the sentences with too many words from other languages, which is common at this globalized era. However, there might be a case that the ratio of the source language is too low, or even the source language is selected incorrectly. So our solution to this is going through the vocabulary and character set used as the training data of the model, calculating the ratio of unknown words and characters, and rejecting the sentences in which the unknown ratio is too high. As Chiho introduced previously, our model can translate the input from web page or document with the style kept. So in the following 2 slides, I would like to show the steps of how tag translation works at the solution level. First, we parse the sentence into a grammar tree to see if it is tagged properly and reject those who fail to do so. After that, we replace those tags with the tokens that our model can recognize. And then let the translation model work its magic. Afterwards, we restore the original tag information back to the sentence. We also have a placeholder to prevent the model from translating too much. While applying the placeholder to the sentence similar to processing tagged sentences, we first replace the elements that should be kept with the placeholder tokens, and again, let the model do the magic, and then we restore the original contents back to the translated sentence. The third strategy for preprocessing we would like to share today is formatting normalization. Sometimes the format of input sentence might look a little bit strange because of, for example, extra spaces or unusual capitalized letters. Such formatting might make the model's understanding worse and affect the translation quality. Therefore, we collected some rules of common formatting issues and added a component to clear them. Here are 2 of the formatting issues we collected, which are capitalization consistency and units of measure. With normalization process applied, models can give us translation results with better quality. The third part of my section will focus on the development process of the on-device translation system. I'll first talk about the challenges to our team and then the system we designed to evaluate the translation models. And after that, I'll wrap up this section by introducing our infrastructure to boost the development. Here are 3 of the challenges we have met during development. The first one is the growth of supported language, which also makes our development team getting bigger. Therefore, we must always consider extensibility while adding new features to our system. For example, some languages might need different logic for segmentation and formatting. The second one is backward compatibility. Compared to cloud service, it is possible that user chooses not to update the service to the latest version, especially for the large system like our translation service, which is composed of several applications. It is possible that the user only updates some of them while others remain in the previous version. Therefore, every time when there is a structure level update, we have to make sure the robustness of the new interface and conduct the integration test on every combination of the applications in the previous and latest versions. The third one might be a common challenge across the topics at natural language processing. The languages we use in our daily life are still evolving, and new words and phrases keep emerging. To make sure the on-device translation keeps up with this pace, we are currently working tightly with linguists, adding new training data and retraining models on a regular basis. Before talking about the evaluation infrastructure, I would like to introduce the rough view of our system architecture, which is designed for high extensibility. As the slide shows, most translation logic is modularized together, with only the interface needing the platform implementation open. Therefore, with the same translation core logic, we have expanded our on-device translation system to Android application running on mobile devices, the Tizen application running on the television, and the command line implementation for the desktop application. Among them, the desktop implementation helps most when it comes to continuous integration and development process. Here is the application of desktop implementation to our evaluation process. We first packed it with a Docker container so that it can work with GitHub Action more easily. As for the flow of our evaluation, we can see from the slides that the flow is triggered automatically when the pull request for an updated model is created. It will download the evaluation test set from another GitHub action and run the translation inference on the Docker container. With the inference result, it will run a quantitative assessment on another GitHub action and return the result back to the pull request. The evaluation infrastructure is just a piece of our work to boost the productivity. Now let's take an overall look at how our continuation integration works when a new translation model comes out. First, it triggers a review bot to check if the new model is named according to the naming convention and the version code is configured properly. The pull request also triggers the evaluation process, which we just saw in the previous slide. After the evaluation result is returned, our infrastructure not only leaves a comment under the pull request, but it also sends the result to our database server, which is used to manage the release history and compare the performance among the models. After the developer makes sure that an updated model works well by referring to the result of evaluation, they can merge the pull request so that our release progress will be triggered. The release progress will then pack the models into the product on the corresponding platform and notify the developers under other departments about the release. This infrastructure is the reason that we can keep collaborating as a huge development team, and it is also the foundation that allows us to keep extending the supported languages to our translation system. So if you have any questions or want to discuss further, come join us at the tech session at Meetup Zone. And thank you for joining us today as we introduce our translations service. See you.